When we're faced with a programming problem, it can be exciting to immediately start thinking about how our solution is going to get turned into code. We want to jump right in and start seeing results. Even if we give the program a little thought ahead of time, jotting down some notes or putting some comments in our program, we'll often want to go right into the process of writing code. We'll start at line 1 and go forward, as though we were writing an essay, but in code. Now, in very simple cases, this can work. We just write one line of code after another, testing along the way until we're done. But most programming requires a more powerful approach, one that lets us take a problem we face and break it up into bite-sized pieces. This insight led to one of the most well-known software development techniques there is, top-down design. Top-down design emerged as a major approach in the 1970s, as software became more complex and applied to a wider range of applications. And it's still one of the main development paradigms used today. For our main program in this lecture, we're going to develop a system that'll let you load and analyze weather data collected over time. But the main point I want you to get from this lecture is not just the specific code we write, or even how we analyze data. The more important lesson is the overall process we use to build the program, a lesson that builds on what we've already seen about the importance of testing and iterative development. For any project consisting of more than a few lines of code, we can always benefit from having a process to follow that makes the task more manageable. Top-down design is one of the most commonly applied methods for developing computer programs. As an analogy, suppose that you're responsible for planning a very large family dinner. Well, thinking about every detail of the dinner all at once can easily become too overwhelming. So instead, you might first think about which courses you want to serve. For instance, you might want an appetizer, a main course, and a dessert. Easy enough. Once that's settled, the next step might be thinking about what dish to serve for each of those courses. For the dessert, for instance, you might choose to have cake, so you think about what's needed for the cake. You need to cook the cake, prepare the frosting, and then put the frosting on the cake. Cooking the cake has a series of steps all its own. Well, this process is an example of top-down design. With top-down design, you begin by looking at the big picture, the top, which is often too much to consider all at once in fine detail. You then break that overall task into a series of more manageable tasks. That is, you work your way down from the top. For instance, if you're planning a big vacation, you might need to plan out your transportation and your hotel and your activities each day. Each of those might get broken down even more. Your transportation might include getting to the airport, flying on a plane, and then getting to your hotel. You could use the same top-down approach for preparing a presentation, writing a book, organizing a home improvement project, and many other kinds of major projects. Top-down design is also a good way of approaching programming problems. When faced with a problem, it helps to break it into smaller, more manageable pieces. If you continuously analyze a problem and break it down into smaller conceptual ideas, eventually you'll reach the point where the idea you need to express can be written in just a single line of code. Using top-down design usually leads to well-organized code, where the purpose of each section of code is clear and concise. So, let's see how we can apply top-down design to our particular programming problem. Here's the setup. Let's assume that we have a file containing some temperatures measured in a particular city over a period of time, and we want to understand something about the weather patterns. What's been the pattern on a birthday or anniversary? What about weather during a week we have in mind for a trip? Here's an example of a piece of the data file that we'll be able to use. This one happens to have data from where I live, and I just copied 15 years worth of data off a website I found. For each day, we'll have a date, the high temperature on that date, the low temperature on that date, and the rainfall on that date, all separated by commas. This type of file is called a comma-separated value, or CSV file. Or it's sometimes just called a comma-delimited file. For data that starts out in Excel or another spreadsheet program, it's easy to use the spreadsheet program to output the data values, separated by commas, as a CSV file. To get weather data like this, you can go to any one of several weather websites. A quick web search for weather data will bring up some websites that will provide this historical data for you. Sometimes they'll even let you download it into a spreadsheet. but at worst, you can cut and paste data into a spreadsheet yourself. Once you have it in the spreadsheet, you can save it to a CSV file. When you're saving it, you should have an option to save it as a .csv file. So, we'll assume that we have this file of weather data, and that it's sitting in our directory where we're writing our Python program to make it easy to find. Our Python program might be called Your Special Day, and we'll set it up to answer some queries about past temperatures on that calendar day. Maybe we want to find the hottest and coldest temperatures on record, the average daily high and low, the largest one-day temperature swing, the high and low in a month surrounding the date in question, etc. So, let's see how we'll design this program using a top-down approach. We want to think about what has to happen in the broadest terms first. At this broadest level, we have three basic steps common to many programs. We read in our data, we analyze our data, and we present the results to the user. Believe it or not, this is the end of the top level of the design. At this stage, we don't worry about how these particular pieces are handled, just that these are the main tasks. Now, usually in design, we want to do a bit more than just sketch out one level before we write code. But notice how some of this can already translate into code. The code that we have here is just 3 comments. That's right, we're not actually writing commands yet, since we haven't really designed any of the low-level details. About all we can do at this point is give the outline of each of the main sections, and we're designating those with comments. Now, these comments that we put in are important. They help us understand what the goal and meaning of a section of code is. Some programmers neglect comments as a waste of time. I mean, after all, comments don't actually turn into any machine instructions. If we leave them out, the code will run exactly the same. Comments, though, are critical to helping people understand programs, including the person writing the program. Comments will help you design the program, and comments will help you remember what's going on when you come back to your code later. I've had chances to go back to code I wrote 20 years ago, and I'll tell you, I wish I'd put in more comments. Even if you think, I'll never see this code again, your comments can still help make sure that your code is following the design plan you had all along. And if there's any chance that you'll go back to look at your code in the future, you'll be glad you spent the time putting in comments. Now, let's get back to our top-level design and try to go one level down. Our first task is to read the data in. So let's think about what we need to do to read the data in, again at a high level. The normal pattern will be to open the file for reading, actually read in the lines of the file, and then close the file. So, let's first look at what we have so far in terms of how it would appear in comments. We're basically taking each level of the design and putting in a comment describing what it does. Now, all these comments can get a little messy, so sometimes it helps to put in some additional characters to help visually separate code, like the sets of 10 hashtags I've put in. Okay, again, we have some pretty high-level ideas, so let's break those down a bit more. We'll start with the reading in data part. To open the file, we need to know the file name, which we'll assume the user is going to give us. Then, we need to actually give the open command. At this point in our design, we're basically at the level of individual lines of code. Each of these ideas corresponds to one or maybe a few lines of code. So we can actually start writing the code now. We'll start by asking the user to input a file name, and then we'll call the open command for that file, noting that we're wanting to read the file. Now, what if you've forgotten at this point how to write a particular command? Well, besides reviewing lectures from this course, there are always online references that I want you to feel ready and willing to use. A good reference for the syntax of various commands is the Python tutorial at python.org. For example, we can find a section on reading and writing files, and then when we're there, we see right at the top a description of the open command. So, we'll write our open command, calling our file that we open infile, and listing the file name and the letter R in the parentheses. So, if you forget the syntax for a specific command, no worries, you can always look it up. Alright, at this point, after we've written a few lines of our code, what's the next thing we should do? If you said, write more code, hold on. First, we should test our code. We want to make sure that we didn't make some silly mistake at this point. In this case, we have just 2 lines of code, so we can run this to see if it seems to work. When we run, we get our message asking for the file. Now we type in the name of the file, which I happen to name datafile1 in this case, and it all seemed to open okay. No apparent errors, so we'll go on from here. Now, note that I had to already have datafile1 created and sitting in the same directory as my Python program. Now, just to make sure it's really reading, we can put in a line of test code just to read in and print out the whole file. Calling infile.read parentheses will read in the entire file. And so by saying print infile.read parentheses, we should be able to see the whole file. If we run this code, sure enough, we see the entire file output to the screen. This line of code where we printed the file was just for diagnostic purposes. So once we're done with the test, we should delete it. Or we can turn our test into a comment by putting a hashtag in front of it. That way, we can see precisely how and where we tested our code. And we can always reactivate that test later on by taking out the hashtag. Once the code is fully working, though, we want to get rid of comments like that so that our code isn't too confusing. Remember, you should be testing all along the way and fixing problems as you find them. Now, for the sake of time, I'm going to skip showing you these tests as we keep going in this lecture. But don't forget that you should be testing regularly. All right, if you've done enough tests, it's time to write some more code, right? No! Next, we should think more about our design. As with any design process, we need to stop and think about our plan before jumping forward and implementing something. We've already completed the file opening, and our next task is to actually read in the data from the file. We'll be reading in line after line, doing basically the same thing. So this is going to mean looping through all the lines of the file. For each of those lines, we need to read in the line as a string. Remember that our input comes in as a string. Then, we need to pull out the individual pieces of data from the string, and finally store them in a list that we can access later. Okay, we'll develop this code in stages. First, we need our loop. We'll loop through the lines of the file with a simple for loop. The for loop that we see here is going to read each line from a file, and it'll be stored in the variable line. Notice that I've also set up an empty list, data list, that we can use to hold the data that we collect. Okay, back to the design again. We need to extract the individual elements from a line that we've read in. Remember what lines of the data file look like? We have a date in month/day/year format, followed by a comma, followed by a high temperature, followed by a comma, followed by the low temperature, followed by a comma, and finally a rainfall amount. Now, I'm going to introduce you to a new command that'll help you process data like this. Let's think about how this command should work. We have a string that has all this data in it. And we want to pull out the first part, the date, the second part, the high temperature, the third part, the low temperature, and the fourth part, the rainfall. These are all separated by commas. So, we'd like to have some command that would let us take the string and get back each of the parts that's separated by a comma. We can do this with a built-in Python command that lets us pull out parts of a string that way. The command is called split. We use it by taking the string name, which in this case is line, followed by a period, and then in parentheses, after the word split, we put the character that tells us how to separate the parts. In this case, we're using a comma to separate the parts. The split command returns a set of values that we can assign to several variables, a, b, and c in this case. The thing it returns is a tuple, and we'll be able to assign the tuple to several values. Let's see an example. Say we had a phone number given with all the parts separated by dashes. The code you see here will help us reformat a phone number into a different form. The split command will help us pull out each part. By putting a dash in the parentheses, we're saying that we want each part that's separated by a dash. So in this case, we get the area code, the prefix, and the suffix. Then we can reconstruct a new string by putting parentheses around the area code. You can also call the split command without saying what the separator will be. In this case, it'll use white space as the separator. White space means characters that don't show up as text. Things like spaces, new lines, and tabs. So in the example, we have a couple of sentences in our source text string. If we call split, it will pull out each word individually. Notice that any white space, including a newline character, will work as a separator. In the end, we get a list of words, although it's important to remember that punctuation like commas and periods is not white space, so it'll become part of the words. Try this out yourself. Let's say we have a greeting like you see here, and we want to print it out. But instead of having the /n for newline, this greeting has NL written in angle brackets, the less than and greater than symbols. How might you print this out so that each of those NL symbols gets treated as a newline? Here's what your code might look like. You can first split the greeting into different lines by using the split command, and the NL in brackets is the separator. Then, just loop through that list, printing each line individually. Okay, let's come back to our main program. In our design, keep in mind that we have two things going on here. We need to split the line up into its parts, and then we need to store each value in the appropriate place, a variable of the right type. So, what do you think the code will look like for the first part of that, actually splitting the line? Remember that our separator was a comma, so the line here, where we call line.split with a comma character inside the parentheses, will give us back the four elements of the line we care about: the date, high temperature, low temperature, and rainfall. Now, we probably want temperature and rainfall values to be numbers, and the split command is going to return strings. So, we can convert these values using the type converter we've seen several times before. Let's convert each of the temperature strings to integers. For rainfall, we'll convert that string to a float. We could also do a little bit more. It might be okay to keep the date like it is as one single string, but it might be better if we had the month, day, and year separated out into separate variables. Based on what we've seen so far, how would you take the date and break it up into a month, day, and year? Yeah, we can use the split command again, dividing the date into its three components. This time our separator is going to be the slash. Then we turn each of those date components into an integer. We still need to put this data for this line into a list, so that we can retrieve it later in the analysis phase. So, we'll create a list with all the data we just found for one day: the day, month, year, low temp, high temp, and rainfall. We'll append that list onto the data list variable that we created. So data list is going to be a list of lists. While we're at it, let's reverse the order of the low and high temperature in our own list versus what was in the original data file. And let's reverse the order of month and day. We don't want to have to stick to the order in the original data. We can store the data internally in whatever order makes sense to us. So, even though the original data had month before day and high temperature before low temperature, we can store it in a different order that makes more sense for us. Here's what the resulting data set will look like for the first several items in the input file. Notice that each value was converted to a number of the appropriate type, and the lists within the bigger list store the data in the order we specified. Now, there's one more thing we need to do in this reading in data part of the overall design, and that's close the file. That's a simple process. It only needs one line of code. Now, at this point, you should have tested your code at several points along the way, especially whenever you finish one section of code. Let's stop for just a second and see where we stand. We had our overall design, in which at the top level we had three subpieces. The first of those, reading in data, had three subpieces of its own. One of those parts had a couple of subparts, and another had even more. We gradually worked our way down from the top to each of those, until in the end we had just one or a few lines of code corresponding to each piece of design. If we look at the code itself, and in particular at the comments that we see in the code, this top-down design is pretty clear. You can see the overall design from these pieces. So, we finished the first piece of the program, and now we're free to think about the next overall piece in our top-down design. We've read in our data from the file, and we've stored it into a list. Now we need to process that list and analyze the results. Remember that our goal with this program is to find out historical data about a particular date. So we'll need one additional piece of input, the date that we're dealing with. Then, we'll need to get the relevant historical data for that date. And finally, we'll need to analyze that historical data to find the info that we care about. In order to get the date from the user, we'll need to ask the user for the month and the day. There are lots of ways we could do this, but to keep it simple, we'll ask for the month, then for the day. So for this design, how would you write the code that reflects this? There will be just one line of code for each piece of the design. We just have a couple of input commands, each time converting the input to an integer. Okay, now let's turn to a trickier part. We want to pull out all the historical data for the date we care about. Remember what the original data file looked like? We've read this into a data list, which is a list of lists. Each of the lists inside has the day, month, year, low temp, high temp, and rainfall. Now, we have a particular month and day we care about, and we want to find all the historic data for that date. What we want to do is go through the data list, and for each of the lists in there, check whether the day and month match the ones that we care about. If so, we'll store that information in a different list. Let's see what the code looks like, but just to keep things simple, we'll focus only on this section of code. We first create an empty list called good data. This is going to hold the data for the dates that match our target date. We then loop through all the data list. Notice that in the for loop, we'll refer to each element of data list as single day, since it's the data for one single date. In the loop, we compare the first two elements of single day, which correspond to the day and month. We compare them to the day and month that the user entered in. If they match, then we take the remaining elements of single day and put them into a new list, which gets appended to good data. So, after we get through this code, we should have a list of the information corresponding to the date that we care about. Now we need to go ahead and analyze it. First, let's figure out some key information about the highest and lowest temperature, and the average high and low. To do this, we'll loop over all the dates and keep track of information as we look at each record. First, we'll count the number of dates so that we can get an average. Now in this case, I know that there are 15 years of data, so this should be 15. But maybe there's a missing day, or we don't know how much data we have, or it's a leap year day, February 29th, or whatever. So we might as well count. Next, we'll keep track of the highest and lowest temperature that we've seen so far. And finally, we'll add up the max and min temperatures, so that at the end of the loop, we can calculate an average high and low. The corresponding code starts by initializing all of our variables that we need for the analysis. We set the sums to 0, and for the max and min temperatures seen so far, we start out by setting them to some extremely low and high values. Obviously, since we set a super high minimum temperature, the first date we encounter will have a lower minimum. Likewise, it'll have a higher maximum than the very low value we start out with. Then, we loop through all the data, and we update each of those values along the way. For every date, we increase numGoodDates. We add the max to our sum of max, and our min to sum of min. We then check to see if the min is lower than the min that we've seen so far, and if so, we update that. We also check to see if the max is larger than the max that we've seen so far, and if so, we update that. After the loop, we calculate the average max and min by dividing the sum by the number of dates. Okay, let's turn back to our design. We've completed all the parts of the analysis. We're going to look at the last of the three major parts, and that's giving the output. This is the most straightforward part of this particular program. We just print out the highest and lowest values that we've seen, and we print out the average, low, and high. The code for this is pretty straightforward. We just have a set of print statements for values that we've already found. So, now we have a complete program. Let's review this. Say we're thinking of having a Halloween party, and we want to know how hot it's likely to be. If we run the code, enter data file 1 for our file, and then 10 and 31 for the date, we find that the temperatures ranged from 45 to 86 on that date, and our average low is around 56, and our average high is around 80. So that tells us that we're likely to have pretty moderate weather. We could easily plan to have outdoor activities as a big part of the Halloween party, even into the evening. Now, we could run this again with a different date. If we were planning something on the 4th of July, it looks like we have temperatures ranging from 67 to 99, with an average low of 71 and an average high of 91. So, we can expect pretty warm weather, And if we're having an outdoor activity, we probably want to make sure there's plenty of shade and ice. Now, in our top-down design, we started by decomposing our program into 3 parts. And each of those got further broken down into parts. But this was not the only way we could have broken up the program. For instance, we could have first asked the user for information, and then done everything else. Instead of asking for the file name just before loading the file, and the date just before doing the analysis, we could have asked for both at the very beginning. Neither way is incorrect. You might have developed your own program along those lines instead. Now, looking at our whole program, we've got about 60 lines of code, and that includes the empty lines and the comments. As computer programs go, this is still considered pretty small, but it's a lot bigger than what we've been looking at so far. So it's worth taking the time to make sure you understand it. What we did was take our overall problem, we decomposed it into the main tasks, reading in data, analyzing data, and then presenting data. And we broke each of those tasks down further. For example, we broke reading in data down into 3 parts: opening the file, reading in lines from the file, and closing the file. And each of those was further decomposed, where possible, until what was needed for any one section was just an obvious few lines of code. So, by using a top-down approach, we had an orderly way of approaching the entire problem. We were able to keep the complexity of the design manageable. And in the end, the actual code that we wrote was almost an afterthought. It was an obvious extension of the last stage of design. Remember, programming is about more than just getting instructions to the computer. It's also about organizing ideas in a logical and precise fashion. Top-down design helps ensure that the ideas expressed in code are in fact organized. It keeps each part of your code at a manageable level. At any one level of the design, you don't have to worry about all the tiny details below, or about the big picture above. You just worry about the level that you're in, and maybe the ones immediately above and below. The idea of taking a problem and decomposing it into smaller parts is a powerful one, and it can make the work of designing software a whole lot simpler. Once you have an overall approach to design, there's another set of programming tools that can make actually transforming your design into code even easier. These tools are functions, and we'll be discussing these in our next lecture. We'll see how we can use not only pre-built functions, but also how we can write our own functions to do whatever we want.